Hello students. Last lecture we have seen the statement of Poisson distribution as a limiting form of binomial distribution, and we have already seen some examples and problems. In this lecture also we will continue with the problems based on Poisson distribution as a limiting form of binomial distribution. See the next example. A machine is producing 4% defectives. What is the probability of getting exactly 4 defectives in a sample of 50 using first part of the problem binomial distribution and second part of the problem Poisson approximation to binomial distribution. So first of all, defective, non-defective, it's a Bernoulli trial. So we will define X as success. Getting defective is my success. So we will define X accordingly. Let X denote number of defectives. Therefore, X follows binomial with n is equal to 50 and P is equal to 0.04%. The probability mass function of binomial distribution is given by probability X is equal to NCX P raised to X Q raised to n minus X. The range of X starts with 0 and it is up to n and equal to 0 otherwise. Then we will replace the parameters in the second step. N and P are the parameters. If P is 0.04, value of Q becomes 0.96. 1 minus P becomes Q. So probability X is equal to X is given as 50Cx, 0.04 raised to X and 0.096 raised to 50 minus X. And in the next part, we can get the exact answer. Probability of X is equal to 4 can be calculated as 50C4, 0.04 raised to 4, 0.96 raised to 46. So the calculations are 2,30,300 into 0.0000256 into 0.152924377. So the product becomes 0.0901593. Now in this case n is 50 and P is 0.04. So as n is very large and P is very small, X will follow Poisson distribution with lambda is equal to NP. Therefore X will follow Poisson distribution with lambda is equal to 50 into 0.04. The product becomes 2. So X follows Poisson distribution with lambda is equal to 2. The probability mass function of Poisson distribution is given by probability X is equal to e raised to minus lambda raised to x upon x factorial. The range of X starts with 0 and we do not have any upper bound and equal to 0 otherwise. Then replace the parameters. Probability X is equal to X is given as e raised to minus 2 raised to x upon x factorial. X will take value 4. So probability X is equal to 4 is nothing but e raised to minus 2 raised to 4 upon 4 factorial. E raised to minus 2 value is 0.135335283 into 2 raised to 4 is 16 divided by 4 factorial is 24. So the answer becomes 0.0902235 and answer with binomial distribution was 0.09015. So both are equal. Next example. A manufacturer of medicine bottles finds that 1% of the manufactured bottles are defective. The manufacturer supplies bottles in boxes of 500 bottles. The drug manufacturer receives 100 boxes from the manufacturer of medicine bottles. Using Poisson approximation, find how many of the 100 boxes received will contain first part of the problem, no defective. Second part of the problem, at least 2 defective bottles. Now bottle will be defective, bottle will not be defective. So it's a Bernoulli trial. So we can apply binomial distribution. So let X denote number of defective bottles produced by the manufacturer. So X follows binomial distribution with N is equal to 500 and P is equal to 0.01 because 1% are defective. So as N is very large and P is very small, X will follow Poisson distribution with lambda is equal to NP, which can be considered as 500 into 0.01. So X follows Poisson distribution with lambda is equal to 5. The probability mass function of Poisson distribution is given by probability X is equal to e raised to minus lambda, lambda raised to X upon X factorial. X range starts with 0 and we do not have any upper bound and equal to 0 otherwise. The range is countably infinite. Then replace the parameter probability X is equal to e raised to minus 5 raised to X upon X factorial. So in the first part we want probability X is equal to 0, which is calculated as e raised to minus 5 raised to 0 upon 0 factorial. So the answer is 0.006737946. But actually in the question part they have asked us to find the number of boxes. Therefore number of such boxes out of N is equal to 100 boxes received by manufacturer of drug is equal to N into probability X is equal to 0. So which is equal to 100 into 0.006737946. So which is nothing but 0.67 boxes. So approximately 1 box. Next part we want probability X greater than or equal to 2, which we cannot calculate because the range of X is countably infinite. So we will have to take the complementary event as 1 minus probability X less than 2. So 1 minus probability X is equal to 0 plus probability X is equal to 1. So X is equal to 0 probability already we have calculated. So we will calculate probability X is equal to 1 as e raised to minus 5 raised to 1 upon 1 factorial, which is equal to 0.006737946 into 5. So the answer becomes 0.033689735. But we want to find probability X greater than or equal to 2, which is nothing but 1 minus probability X is equal to 0 plus probability X is equal to 1. So which is nothing but 1 minus 0.006737946 plus 0.033689735. So 1 minus 0.0404276. So the answer becomes 0.9596. But we are expected to find the number of boxes. So therefore number of such boxes out of 100 boxes received is equal to 0.9596 into 100. So the answer is 95.96 boxes. So approximately 96 boxes. Next example. Assuming that the probability of fatal accidents in a factory during the year is 1 upon 1200. Calculate the probability that in a factory employing 300 workers, there will be at least 2 fatal accidents in a year. So let X denote number of fatal accidents in a year. So X follows binomial distribution with N is equal to 300 and P is equal to 1 upon 1200. So as N is very large and P is very small, X will follow Poisson distribution with lambda is equal to NP, which is equal to 300 into 1 upon 1200. So answer is 0.25. So X follows Poisson distribution with lambda is equal to 0.25. So the probability mass function of Poisson distribution is given by probability X is equal to e raised to minus lambda, lambda raised to X upon X factorial. The range of X starts with 0, 1, 2, 3 up to infinity and equal to 0 otherwise. Then we will replace the parameter. Probability x is equal to x is given as e raised to minus 0.25, 0.25 raised to x upon x factorial. We want to find probability x greater than or equal to 2, which cannot be calculated directly because the range of x is countably infinite. So we will take the complementary event as probability x less than 2. 1 minus probability x less than 2. So which is nothing but 1 minus probability x is equal to 0 plus probability x is equal to 1. So let us see how to find probability x is equal to 0. E raised to minus 0.25, 0.25 raised to 0 upon 0 factorial. So the answer is 0.778800 because 0.25 raised to 0 is 1 and 0 factorial is also 1. Then probability x is equal to 1 is calculated as e raised to minus 0.25 into 0.25 raised to 1 upon 1 factorial. So if you multiply the first probability with 0.25, you are going to get the second answer 0.194700195. So therefore probability x greater than or equal to 2 can be considered as 1 minus 0.7788 plus 0.194700195. So this total becomes 0.9735. So the final answer comes out to be 0.02649. Next example. An automatic machine makes clips from coils of wire. On an average, 1 in 400 per clips are defective. In the paper clips are, if the paper clips are packed in the boxes of 100, what is the probability that any box of clips will contain first part no defective, second part one or more defective, third part less than 2 defectives? So let x denote number of defective clips. So x follows binomial with n is equal to 100 and p is equal to 1 upon 400. So as n is very large and p is very small, x will follow Poisson distribution with lambda is equal to np. So value of n is 100 and p is 1 upon 400. So the answer becomes 0.25. The probability mass function of Poisson distribution is given by probability x is equal to e raised to minus lambda, lambda raised to x upon x factorial. Range of x again starts with 0 up to infinity and equal to 0 otherwise. We'll replace the parameter. Probability x is equal to x is given as e raised to minus 0.25, 0.25 raised to x upon x factorial. Now probability x is equal to 0. Again we have to calculate e raised to minus 0.25 into 0.25 raised to 0 upon 0 factorial. The answer is 0.7788. Next part of the problem. Probability x greater than or equal to 1 is nothing but 1 minus probability x is equal to 0, which is nothing but 1 minus 0.7788. So the answer is 0.221199. Then probability x less than 2 is written as probability x is equal to 0 plus probability x is equal to 1. So the answer becomes 0.778800 plus 0.1947. See, 1947 we have calculated here. Probability x is equal to 1 is nothing but e raised to minus 0.25 into 0.25 raised to 1 upon 1. So 0.7788 multiplied by 0.25 will give you 0.1947. So probability x less than 2, the answer becomes 0.778800 plus 0.1947. So the final answer is 0.973500. So these are the three answers. First answer, probability x is equal to 0, which is equal to 0.7788. Second answer, probability x greater than or equal to 1, the answer is 0.221199. And third answer, probability x less than 2 is given as 0.9735. Next example. Suppose that the average number of accidents occurring weekly on a particular stretch of highway equals 3. Find the probability that there is at least one accident this week. So let X denote the number of accidents occurring on the stretch of highway during the week. So X follows Poisson distribution with lambda is equal to 3. Probability X, the PMF of Poisson distribution is given by probability X is equal to e raised to minus lambda, lambda raised to X upon X factorial. X takes values from 0 to infinity and equal to 0 otherwise. Probability X is equal to e raised to minus 3, 3 raised to X upon X factorial. We want probability X greater than or equal to 1, which can be written as 1 minus probability X is equal to 0. So probability X is equal to 0 can be calculated as e raised to minus 3, 3 raised to 0 upon 0 factorial. So the answer is 0.049787068. But we want to have probability X greater than or equal to 1, which is equal to 1 minus 0.049787068. So the answer is 0.9502129. Next example. The number of monthly breakdowns of a computer is a random variable having Poisson distribution with parameter lambda is equal to 1.8. Find the probability that the computer will function for a month, the first part of the problem, without a breakdown, second part with only one breakdown. So let X denote number of breakdowns of a computer. So X follows Poisson with lambda is equal to 1.8. The probability mass function of Poisson distribution is given by probability X is equal to e raised to minus lambda, lambda raised to X upon X factorial. The range of X starts with 0 and we do not have any upper bound and equal to 0 otherwise. So probability X is equal to X is given as e raised to minus 1.8, 1.8 raised to X upon X factorial. We want to find probability X is equal to 0, which is equal to e raised to minus 1.8, 1.8 raised to 0 upon 0 factorial. So answer is 0.1653. Then probability X is equal to 1 is nothing but e raised to minus 1.8 multiplied by 1.8 raised to 1 upon 1 factorial. So 0.297537. Next example. The monthly worldwide average number of airplane crashes of commercial airlines is 3.5. What is the probability that there will be at least 2 such accidents in the next month? Second part of the problem, there will be exactly 4 such accidents in the next month. And third part of the problem, there will be at most 3 such accidents in the next month. So let us define X as, let X denote monthly number of airplane accidents in the commercial airlines. So X follows Poisson distribution with lambda is equal to 3.5. The probability mass function of Poisson distribution is given by probability X is equal to e raised to minus lambda, lambda raised to X upon X factorial. The range of X starts with 0 and we do not have any upper bound and equal to 0 otherwise. So probability X is equal to X is given as e raised to minus 3.5, 3.5 raised to X upon X factorial. In the first part of the problem, we want to find probability X greater than or equal to 2. So which is equal to 1 minus probability X less than 2, which can be written as 1 minus probability X is equal to 0 plus probability X is equal to 1. So probability X is equal to 0 is equal to e raised to minus 3.5, 3.5 raised to 0 upon 0 factorial. So the answer is 0.030197383. Then probability X is equal to 1 is calculated as e raised to minus 3.5, 3.5 raised to 1 upon 1 factorial, which is equal to 0.030197383 into 3.5. The answer becomes 0.1056. And probability X greater than or equal to 2 can be written as 1 minus 0.030 0.19 plus 0.1056. So the total answer becomes 0.864119. Then second part, we want probability x is equal to 4, which is nothing but e raised to minus 3.5, 3.5 raised to 4 upon 4 factorial. So which can be considered as 0.030197383 into 150.0625 divided by 24. The answer is 0.1888122. Then third part, we want probability x less than or equal to 3. So we will need probability x is equal to 0, which already we have calculated. Probability x is equal to 1, probability x is equal to 2, probability x is equal to 3. So the things which we don't have, that is nothing but probability x is equal to 2. We will calculate this as e raised to minus 3.5, 3.5 raised to 2 upon 2 factorial. So the answer can be written as 0.030197383 into 12.25 divided by 2. So the answer becomes 0.184958. Then probability x is equal to 3 can be written as e raised to minus 3.5, 3.5 raised to 3 upon 3 factorial. So 3.5 raised to 3, the value becomes 42.875, and 3 factorial is nothing but 6. So the answer can be calculated as 0.030197383 into 42.875 divided by 6, which is equal to 0.215785. Now for getting the answer probability x less than or equal to 3, we will add all the 4 values: 0.030197383 plus 0.1056 plus 0.184958 plus 0.215785. So the final answer becomes 0.536540.